Hello, this is Barrett Roth. I am the director and co-founder of Circular Economy Manufacturing. Our startup company is trying to change the way the world makes things. We're doing that by creating a solar-powered MicroFactory that recycles single-use plastic into durable products. In this interview, Mark Ventura, one of our team's engineers and brilliant rocket scientists, explains the structure and functionality of our MicroFactory. The interview is being conducted by one of our interns, Mackenzie Fisher, a mechanical engineer from Stanford University. Hope you enjoy it.
So, would you tell me a little bit of background on yourself and your career?
Sure. I'm from the Northeast. I grew up in New Jersey. I have a degree in mechanical engineering from the University of Pennsylvania, and I have a master's degree in engineering from Purdue University. I've mostly worked in rocket propulsion for my career. I came to California to work on the space shuttle program, which I did for about 10 years and various other programs. And then I decided I wanted to go out on my own, start my own business, which I did, and I've been doing that for about the past 20 years. We do mostly research and development in aerospace and defense, as well as in energy systems and industrial and commercial products.
Very cool. And so how did you meet Andrew?
Well, Andrew and I met on a project, so I had had some affiliation with the Boeing company here in Southern California, and Boeing was working on a solar program trying to leverage their use of their multi-junction space-based solar cells. And they were out trying to develop a terrestrial, large-scale solar power system. The management at Boeing knew that I was very competent at doing these sorts of esoteric, unusual product development projects. So they asked me to come in and act as a kind of a senior engineer to solve some of the more unusual design problems for the program. Andrew turned out to be a young engineer at the time, responsible for designing the two-axis drive element, which would take the solar panels or the solar concentrating elements and track the sun in two axes. And I was there more as a senior engineer to help him develop that system.
Very cool. And then what led to the decision to start your own business?
Well, I've always wanted to run my own business. My family has had businesses. My father has a business in New Jersey. He repairs and sells bicycles. I worked for him as a teenager and through college. I ran the business a couple of summers, and I thought this is pretty neat. It's kind of neat to run your own business, come up with products, come up with ideas, make money. And I thought, well, I'd like to try to do that. And I kind of, through happenstance, ended up in the rocket propulsion industry. And I started seeing things about it that I thought would be interesting to change. I could try to make it better. I was probably one of the very early people in what we now see as the commercial rocket industry. So I started doing this sort of activity on my own quite a while ago. And I had identified certain areas that I thought would be of interest to try to improve. And so I thought, well, I had a chance, so I left and then started the company.
Very cool. And then why did you want to get involved in this project, and what are you most excited about with regard to this project?
Well, I was very happy to hear that Andrew was involved in it, because I respect and trust his judgment from having worked with him. I do get approached by many people with a lot of crazy ideas, so you do have to look at projects carefully to see if they make sense. So Andrew had already spent quite a bit of time doing that, and that was very helpful. So I thought, okay, this seems like a real project. I met Barrett, of course, and then that was very helpful because he's a very straightforward, trustworthy type person. And he had a vision and an idea, and he was thinking about how to make it economically viable, and I find that very attractive. The other thing that, of course, this is renewable energy and recycling type materials. That's kind of the idea behind the basic product, but you need something that actually makes that story make sense, which Barrett had, in my opinion, carefully thought through. So I felt like, yes, this looks like it's a reasonable strategy. And of the things going on in this project, the recycling part I'm personally quite interested in. The business that I started in rocket propulsion was environmentally preferred non-toxic propellant chemistry, because there's a lot of things happening with that area that are not as good for the environment as they could be. So the idea of pollution and trying to minimize waste and things like that, that's been something I've had an interest in since I was very young, and it's something that I've been pursuing through my own company for a long time. So I really like it, and I also like that this is trying to solve the problem with a viable economic solution. Because if you can do that, the problem is solved, and that's the great part. If you can find a way to economically fix it, it gets fixed.
Yeah.
So I'm hopeful. We'll see how it works, but it's got the right strategy behind it.
Yeah. That seems to be like the barriers. People want to do good, but if it doesn't make sense from a business perspective, then
well, then it doesn't, and then you have to do it for some other reason, like maybe the government's going to pay for it, or maybe you just choose to do it because you think that it's something that you want to do. But ultimately, you're going to get stuck if the government doesn't support you, or if you're not a wealthy person that can afford to spend the money. Then you can only go so far. But once it gets economic legs, then it's kind of a self-sustaining thing unto itself, and it can be done. It just takes work.
Yeah. I think you kind of answered this, but if you have anything else, just as an engineer, how important do you feel it is that we start designing for closed-loop systems?
So I have particular concerns about a lot of what's happening in our economy, where we're generating a very large waste stream. So especially now with some of the new forms of retail, we have large amounts of packaging, so you get a lot of paper, you get a lot of plastic, you get a lot of plastic films. These are not very recyclable, and they're just accumulating. They also, unfortunately, the plastics, which are very recyclable materials in general, tend not to be. They just tend to go to the landfill. So we are recycling some plastics, but still there's huge amounts of plastic waste, which is just getting piled up. Another one which is similar but not addressed by this project is electronics waste, but it has the same basic problem. It's accumulating. It's not being rendered. In that sense, a little bit like plastics, we're taking materials out of the earth, we're concentrating them, we're using them, and then we dispose of them, but they kind of hang around. They're now we've dragged them out of the ground and we're living with them. And that just gets worse and worse and worse, and it gets worse, for subsequent generations, because it's just not the environmental. I mean, the electronics waste doesn't really break down. Plastics break down a little bit, but they're still pretty slow. So we're kind of making a big problem that's just getting worse every day, and the world economy is becoming more so like that. So, for example, the parts that I've been receiving to work on, everything's wrapped in plastic. It's just chronically there, and it's just getting bigger and bigger. So I think it's a huge problem that some sort of solutions have to be found for it, or it's just going to be like Wall-E.
Yeah,
The movie, right? It's really scary, but it's a really well done movie to show the future.
Yeah.
So yeah, that's a big motivator for me in this kind of a project.
Awesome. Could you walk me through the basic steps of rotational molding?
Sure. So rotational molding is a method for making plastic parts by melting the plastic inside of a mold. So the mold acts as a negative. It's like a shell. So you can imagine maybe a two-piece mold that you put together, and on the inside will be the shape of your part. And then you put plastic material inside the mold, like pellets or powder or shavings. Like in our case, we're going to be trying to work with, say, shredded plastic. We'll put that inside the mold, and then you heat the mold up, and as you're heating the mold, you're rotating it. And you want to rotate it a lot. You want to rotate it in as many axes of rotation as possible. So instead of, you just don't rotate it like this, but you'll also rotate it like this simultaneously. And what happens is the part will kind of start going crazy. It's rotating all over the place. And as it's doing that and it's heating up, the plastic will melt and it'll start to adhere to the outside surface of the mold, and it'll form a thin layer of plastic on the outside surface. And it'll fill in all the feature details on the surface of the mold. So if the mold's got a little detent or a ridge, the plastic will flow into that feature and fill it. Then, after the plastic is fully melted, you pull the mold out of whatever your heat source is, and you let it cool, and you let it continue to rotate. And as it's cooling, that plastic basically melts on the outside of the mold. Once the plastic's fused adequately, you can break the mold apart, pull the part out, and then you can start the process over again. Put more plastic in and rotationally mold it again. So it's a relatively easy way to make a thin-shelled plastic part with a plastic that melts, which is a thermoplastic, melting plastic.
So how is the mold heated in our case, and how is it traditionally done?
So we're going to heat the mold using electric heaters, and those electric heaters will be potted or embedded or pressed into the mold. So if you can imagine the mold, like say it was a shell, the outside shell will have some thickness to it. We're going to put some holes or ports into that shell, and then heater elements, which would look like, say, rods, will get pressed into that shell, and then electric power will go to the heater and heat it up, which will then heat the structural mass of the mold. The electric power will come from a solar source. There'll be some tricks on how we get it from the solar source to the mold, but that's the basic idea there. Normal rotomolding, the mold is rotated and it's placed inside of an oven. And that oven could be heated by whatever. Could be natural gas, could be electric heaters, but it's basically using some sort of an oven-like furnace, and the entire mold is inside of it while it's rotating around.
Very cool. How does rotational molding differ from other molding processes, and what are some of its benefits and strengths?
So rotational molding, as I described it so far, you can imagine this mold which is moving around and the liquid adheres to the outer surface. The mold only creates features on the outside of the part. The inside of the part is a relatively flat, smooth surface. So if you had feature elements, like you had a little hole or a dimple or a texture, if you had anything that you wanted of specific interest, that would have to be on the outside of the part. The inside of the part will look very dull. It'll be relatively flat. Sometimes there's a little bit of a waviness in the surface because that's what the plastic looked like when it was fusing and it solidified. So basically rotomolding is good for a thin shelled part where the outer surface is the surface of interest. Other molding techniques like injection molding, you'll have a mold and then you'll force liquid plastic into the mold under pressure, and some of the plastic has to come out in various places, but you're basically pushing hot plastic into it. With an injection mold, you can have features that are well controlled on both sides, on the inside and the outside, or depending upon what the mold type is. So injection molding is preferred for certain types of parts that would need that, where rotomolding couldn't do that. Injection molding, I believe, is also far superior in cost when your volumes are large, but the tooling cost is substantial in injection molding. So it's in the world of molding, you'll look at specifically what your plastic part is supposed to be, and then decide what molding process would be most appropriate. Injection molding is perfectly fine. Conceivably, we could also make a solar-powered injection mold system too, right?
Yeah.
Same concept, but the particular parts that we're interested in now, they're most suited by rotomolding.
So we spoke about how the mold's heated and kind of arriving at that idea of just heating the mold versus sticking it in a large oven. Could you speak a little bit to the complexity of heating just the mold with all the rotating parts?
Sure. Right. That's where there's a little bit of cleverness involved in this, because To do a typical rotational cast or mold process, you need to rotate the mold in at least 2 axes. And what that means is you can imagine the mold initially is rotating about this axis. Right? That's fine. It's spinning around. But we also want to rotate it about this axis. And so as we're rotating it like this, it's also rotating like this. And the way we've done that is we have 2 frames. We have an outer frame, which rotates in 1 axis, and then inside that outer frame is an inner frame, or a second frame, and it rotates while connected to the other frame. In order to do this, both frames have to have a drive mechanism. So the first frame drive mechanism is relatively easy, it's just taking something and spinning it. But the second frame's drive mechanism, it's rotating, it's spinning around. So we have to get electric power into the drive axis for the inner frame. In addition to that, the inner frame is rotating, and inside of that is a mold, and the mold has electric heaters. So we have to pass, the simple way to describe this is, we have to take electric power, a substantial amount of electric power, and we have to make it go through 2 different rotating axes that are actually 90 degrees to each other. So it's not something, you can't just plug in a wire and do this because it's just going to get all tangled up. So what we've done in order to make this work is we have something called an electrical slip ring, which is a electrical joint which rotates. So you can pass electrical power through a rotating joint. Now in order for that to work, the electrical slip ring has to be on the axis of rotation. The only way to make that work is that we have to have a drive mechanism that's got a hole in the center. So there's 2 key things to make this work. We had to come up with a drive mechanism that was strong enough to hold all of this equipment and the mold and the plastic and all the drives. It had to have a relatively large hole through the center of it, which is a little weird. And then we had to have a slip ring that would fit inside that hole, so that we can pass the electric power through the rotating axes twice, the first axis and the second axis, in order for it to get to the mold.
Okay, so now on to more of the solar panels, like we were just talking about. I think this kind of plays along with it. So while consulting with Boeing as a chief engineer, you developed the highest performing concentrating solar photovoltaic system, which required a 2-axis mechanism to accurately follow the path of the sun. Could you tell us a little bit about that?
Sure. So the Boeing company, as I mentioned earlier, was trying to come up with a concentrating solar photovoltaic system, and they were trying to use their very high performance multi-junction space-based solar cells in terrestrial applications. Now these solar cells are extremely efficient, they're very nice, they're very, very advanced technology, and they're also very expensive. So economically they don't really work. But they thought, well, what we can do is we can concentrate the light on the solar cell, and then we can make the solar cell really small, really tiny, and you use a large optical device. In their case, they were using mirrors to concentrate all that light onto the solar cell, and then you have a very tiny, expensive solar cell and a very large, cheap optical element. And these optical elements are made out of plastic. They're similar to like headlamps in a car. They're easy to mass produce. The economies of scale are readily available for that type of a product. So that was kind of the idea. But in order for that to work, you have to very accurately track the sun because of the direct normal irradiance problem. The optical element must be pointed exactly at the sun. And the sun, as the sun moves through the sky, they say rises in the east, sets in the west, but it also moves up and down with seasons. So you can imagine the sun is like an arc through the sky, right? And then in the summer the arc is higher, and then in the winter the arc is much lower. So every day this arc of the sun is going up, and then it's coming back down depending upon what the season is. So if you want to track the sun, you need to track it both as it rises and falls daily, as well as how the inclination of that arc moves seasonally. So in the solar world, Some solar panels are fixed, like what you might put on a roof, and then there's also solar products that only track the daily. It's a single axis mechanism that just follows the basic movement of the sun, which is quite effective, but not good enough for the concentrating solar options. So we had to have the 2-axis system that would arc through the sky. Boeing was also trying to work towards large-scale, utility-type, big power plants. This part of the energy industry is very low cost. It's very, very challenging to make anything work in that domain space. So the tracking mechanism, this 2-axis tracking mechanism, had to be extremely cheap. So we put a lot of effort into looking at all the different sorts of ways one might consider tracking and trying to come up with a solution that would economically close. And what we learned from that was one of the key features to that was what are called slewing drives, which are these large bearing gear mechanisms which have a big hole in the middle. And they're very stiff, they're very strong, and they're very cheap, and they're very effective at what they do. So that was a key part of what made that product viable for Boeing, how we were able to get that part of the system to have economic value. It was my opportunity to learn a lot about slewing drives. It was also when I got to work and meet with Andrew on said same slewing drives, and it's those sorts of drives that we saw that also would fit into this project, albeit this is an entirely different application that has no bearing on that particular style. We're using them in a completely different purpose, but functionally they're meeting the need.
There's just some circularity there for sure.
Oh yeah.
I was like, I think that's what we called what you guys were using for the joints too. Okay, so we kind of already spoke to this. If there is extra energy, will it be stored? If so, how?
So the system that we're putting together right now will have various different options. So one will be storage. So if we do have excess energy, we'll be able to put that into some amount of storage. And that's kind of something you can do a la carte. You can have a lot of storage, you can have little storage. The amount of storage that you're going to want will probably be some optimal based upon your location. You can look at how much storage you're going to need. Like say it's going to be cloudy for 2 days or 3 days. How many days of power would I like? So the system is going to be developed to have some storage capacity. Also depending upon the location as well as the local rules or regulations or laws, the system may also be grid tied, in which case it'll be able to also port energy into the grid and pull from it as required, and there'll probably be some possible net metering with that as well. But the current architecture will permit storage of excess power as well as export of excess power, and that'll probably become project dependent as well. But yeah, we'll be storing some of the power.
That's cool too, how you can vary it by region. Like if we were to expand to like a more sunny place, like maybe we don't need as much storage.
That's right. I mean, so you should always, if it's a business, you'd be doing the economics. You would buy the amount of storage that's appropriate for what you're doing. If you don't need it, then you don't do it. If you do need it, then you have to do it.
Yeah. Cool. So then we're also using a shipping container, and Barrett told me that you use shipping containers in your work in the desert, and kind of the thought process behind using the shipping container and the benefits of that.
Okay, so I do a lot of work remotely in desert environments because of some of the work that we do. We have done some solar work in the desert, but we also do rocket engine testing, and it's a little dangerous, and so we want to be far away from other people. So we'll go to some remote location. That location may have a fenced perimeter, it may not, it doesn't really matter, but we'll go out and do work, and we need some means to conduct work. We want to get out of the sun, we need to store things, we may want to protect our equipment from the elements, And we found that shipping containers are a very nice, cost-effective means for containing stuff, safely storing materials, because people can come and take things or damage things when you're not around. They're pretty good at protecting stuff from the environment. They're fairly weather tight. They're very cost effective for what they are, and they're relatively easy to modify. So you can put a wind turbine on them, or insulate them, or a door or a window, or paint them, put shelving or lights in them. So we've done all of that sort of stuff with the containers that we've worked with, and we find them kind of as a great utility type item that's effective and easy to deploy into just about any place you could imagine. And there's people and businesses out there that currently do this sort of activity in converting containers to whatever you would like. So they're a very useful tool for this sort of activity, and this would be very nice with this. This machine could be readily put inside of a container and easily placed wherever you would want to use it.
Very cool. I think that's it.
Thanks for joining us. I hope you enjoyed that interview with Mark Ventura. He's been terrific in building our first MicroFactory. You can follow all of our progress on our social media channels and subscribe to our newsletter for the first looks at our latest developments. So stay tuned for more content. Thank you.